Okay, so last last day we started this theorem, which will basically be a depth 3 circuit lower bound for determinant and permanent, and it will be exponential. Okay, so this is an exponential depth 3 circuit lower bound for determinant and permanent. The only caveat is that we have to assume the field to be a small field, a very small field. Okay, so we'll in fact assume that the field size is constant. We'll see in the end of the proof that proof can afford Q to be slightly smaller than log of D, but not much more. So certainly when Q is square root of log D, we'll still get a bound, lower bound, but if Q becomes larger, then the proof will break down. It will give a trivial lower bound. So the idea will be to consider a matrix, and the rank of that will be a measure for polynomials, and so that matrix is MK C comma A. C is the polynomial. So matrix has rows indexed by k order derivatives and columns indexed by points in a subset A of the space Fq to the n. So we are just looking at derivatives at points of a given polynomial and the rank of that matrix. So the upper bound lemma that we proved, nearly proved, is basically saying that there is an A and there is a measure of this type which is small on the circuits, depth 3 circuits. Okay, the measure will be at most SQ raised to tau. So any questions in the proof of this lemma?
So what was the significance of 8q? Why did you take 8q?
Oh, this was from Chernow bound. This should come from, so we have taken k to be tau over 10q. So that 10 actually gives you 8 in the probability. So this value of k, 10q, is actually what is giving you 8q in the exponent here. So you can ask why are we using 10q. So that will be just to suitably set tau and k. So to define the measure, we need a k and an a. So how we will pick it will be clear in the end, because in the end we want lemma 1 upper bound and lemma 2 lower bound. We'll invoke them together to get the final exponential lower bound. So we have to take care of those both the parameters in lemma 1 and parameters in lemma 2. So these constants and this, even this form of tau divided by 10q is so that all that comparison works. Right, so we had completed lemma 1, almost completed. Let us finish it now, the remaining small part. So we were looking at the case when we are just trying to study the measure on product of linear polynomials, which is this t. Moreover, the hard case is when the rank of these linear factors is large, bigger than tau. So in that case we have to argue that so in that case the set A will be used. The reason to have this set A in the measure was exactly for this case. So we'll argue that if we had picked a random point in the space fq to the n, then with a decent probability, not only will t vanish, but even its kth derivative will vanish. Okay, so basically t will have roots of multiplicity k, in fact more than k. Yeah, so that basically follows from Chernow bound, because look at this line. So we have shown that the number of LIs, the factors of t that vanish at a random point simultaneously, this is expected to be r over q, which is tau over q. So the probability that it is 10% of that, right, that is this probability. So the probability that this actual number in an experiment comes out to be 10% of the mean is expected to be very small, and quantitatively it is this e raised to minus 1/8 of the mean. Okay, so this 1/8 is coming from this 10% that we had chosen of the mean. And right, so from all that we deduce this line, that these ETs are the erroneous, are the bad A's, okay, on which the number of LIs that vanish are less than 10% of the mean. So those bad A's define ET, and since you have many T's, you have at most S many T's, so take the union of all these bad sets. So that is being done here. So if you pick an A that is not bad, then all these T's, kth derivatives will vanish at the point. Okay. And so now once you notice that the union of ETs is small, the remaining points are many. Okay, there is a huge number of points A's such that all the derivatives vanish of all the T's. Okay, so let us just work that out. So let us call this union ET as E. Of course, in this case we are only considering multiplication product gates T with high rank. Others we have already handled. So this has size at most, so they are S many times what is the size bound on ET? Well, Q to the n is the whole space times the probability. So probability is essentially falling as 1/8 of the mean, right? So it's minus tau by 8q in the exponent. E is the natural log, so it's around 2.8. So certainly this is falling exponentially. It's half raised to tau over 8q. Right. So if you look at the density of this, so divide this by q raised to n. So that density can be made extremely small. It can be made tending to 0. You just have to pick tau to be big enough as a function of s, log s. And the good points will be complement of this. So this zeroes out every function in kth order derivatives. I pick any kth order derivative of t that will vanish for these t's. So for high rank t's, uh, every kth order derivative will vanish uh, for every point in the space subset A, right? That's the final thing, and this set is this is almost everything. So this implies that gamma k a c. So now let us look at the measure. So when you look at the measure, what does it depend on? Which TIs will it depend on? So this measure is actually just killing high rank TIs, right? So it only depends on low rank TIs. So this is contributed by only TIs of rank less than tau, which means what? Which will give you an obvious upper bound on the measure, because for for a low rank T, the measure comes out to be q raised to tau, and there are at most s many. Right, so you have shown the upper bound. You wanted to show this SQ tau, and this is what we get. Right, so now you can see that this whatever we did was actually quite natural. We identified these TIs of high rank, we'll kill them by evaluation, and what remains is low rank, and their contribution cannot exceed q raised to tau, s times that. Okay, any questions? So now let us move to the lower bound lemma, which will be for a very specific polynomial. What we currently did is for any polynomial computable by depth 3 circuit, size s. So next we understand the measure for determinant and permanent d cross d. So number of variables is d square. This will be lemma 2 for any subset so we have to say something about the size in the hypothesis. So what we would want to say ideally is that it is the whole space, but since in our lemma 1 we have seen that E could very well be smaller than the full space, so we'll at least need this promise that it's sufficiently large. Okay, so this little o of 1 is saying that the difference of, this density, if you look at the density, then 1 minus the density is tending to 0 for increasing n. Okay, so the density is nearly 1. So with this promise, we can show that measure is huge. So measure of determinant is d choose k square. Is the statement clear? D choose k. Okay, so since we have not really fixed k yet, so it may not be clear why we are saying this. We are saying that this is large. So think of k as d by 2. Right? If you think of k as d by 2, then this comes out to be very close to 2 raised to d. So that's so. So essentially, the measure is 2 raised to d, and if you remember the original theorem, the final theorem which we want to show, we want to show that S is something like 2 raised to d. So that we will actually get because of this d choose k square. Okay, this is the reason for 2 raised to d. So yeah, so this is a property of another property of determinant, that this matrix of derivative at points has large rank, as big as 2 raised to d. Yeah, if we could have made this d raised to d, if this expression was something like d raised to d, then we would have gotten a really optimal lower bound on S. But we cannot improve this. So for determinant we cannot improve, and also for permanent. So right, so what we have to do is consider the rank of the matrix Mk determinant comma A. Right, so again recall that the rows are k order derivative operators and columns are points, and the points are nearly all of the space q raised to n. Yeah, so how do you lower bound this rank? It is a huge matrix.
Most k order derivatives will be determinants, and determinants are low degree, so they'll probably not vanish on points.
Correct, but that is not enough.
Yeah, but so we can't use the previous techniques.
We have to say something about the rank of this matrix. So even if this matrix every entry is non-zero, the rank would be 0. So well, cannot be 0, it 1. The rank can be as small as 1. Yeah, so how do you show that actually the rank is large? So the best way known to us is identify a triangular structure. So in your matrix, identify a triangular matrix, and then the size of the triangular matrix is a lower bound on the rank. Right. So which derivatives should you take? Which rows should you take basically, so that the submatrix looks triangular? Right. So that is the thing to think about. So an order k derivative which will obviously be a partial derivative of determinant d is, so it can happen that just formally the derivative vanishes, right? So for example, if you differentiate your matrix by first by x11 and then by x12, or by x11 and again by x11, right? So these will just formally vanish. So there is no point looking at evaluations because formally it has vanished. Otherwise, what will you get? If it is formally not vanishing, then what is this? It's a minor, right? So it's a minor. It's a determinant of a submatrix. So it's an order d minus k minor. So we'll focus on this, right? So basically a row corresponding to this minor I mean, a row is then just this minor being evaluated at almost nearly the whole space. Yeah, but actually, unfortunately, still there is no signs of a triangular matrix, triangular submatrix in this, right? So probably that will not work. We'll do something else. So since determinant D, so how many D minus K order minors are there? It's a D cross D matrix. So D choose D by K, D choose D minus K, each for row and column choices. So it's square. That the rank of, if we took A to be everything, the whole space, then do you know the rank of this measure matrix? So we are taking it to be A to be everything.
It will be higher, right?
Yeah, so my claim is that then it is this number of minors. Okay, then it will be just these exactly. So all these order D minus K minors, when you consider the rows in this measure matrix, they are linearly independent. Assuming that no point is missing in the column. Column has all the points.
I guess that's because you can find the point where only that minor does not vanish.
Exactly. Yeah. So because if A was everything, then you can identify a triangular submatrix. In fact, diagonal. Right. So this will be the proof. So it's not very important, but let us anyways sketch this. So can pick a point alpha bar in FQ to the n such that column alpha bar has exactly one non-zero entry in this matrix at the desired row. Okay, so at this row which corresponds to order D minus K minor. So you pick your desired or your favorite row, and for this minor you can choose a column alpha bar.
So one thing that confuses me is if you have like a minor, can you make all of the minors that are contained within this minor 0 but still make this non-zero?
Why do you say contained? They all have the same order.
So
They have all.
this will be a lower rank. This rank will be a lower bound, right, of this matrix? Because here we're just looking at the minor. Oh wait, okay. We're considering only derivatives, exact K derivatives.
Exactly
not
K,
less than equal to.
not less than. Right. So this alpha bar will just be. I mean, you look at a M cross M matrix, symbolic matrix. Just set everything to 0 except some variable 1. Right. So except one set everything to 0.
And then minor to one.
No, no. So yeah, or just set the diagonal entries. Yeah, make it basically identity matrix. To put it simply, just set it to identity matrix, and then yeah, so that will give you a extended alpha bar. When you extend this idea, you will get alpha bar. And then as a small exercise, show that for this setting of variables, no other order d minus k minor survives.
Singular zeros.
Right. So it's a small exercise just by the definition of determinant. So that's it. So this this is the idea. So you have, using alpha bars, you have this way to get a sub matrix which is diagonal and is full rank. So you get d choose d minus k whole square. Right. So this is a simple idea, but this has no utility for us because we don't have the whole space. Right. In fact, we might be missing a fraction of q raised to n many points. So if we miss those, if the good alpha bars have been missed, then this proof idea doesn't apply at all. But our A is not fq to the n. So the above idea fails. So what do you do? So what we will do is the next best thing, which is study the linear combinations of the rows. Okay, so basically try to show that and first of all, the dimension of this matrix, the number of rows in this matrix is how much? D choose d minus k whole square, right? So you want to show that all these rows are independent. So if you take an arbitrary linear combination, non-zero linear combination, and you show that there is some alpha bar at which this linear combination does not vanish, right? So it will mean that the rows are independent, right? Because you started with an arbitrary linear combination. So for an arbitrary linear combination, if there is some alpha bar such that this linear combination is non-vanishing, then it means that the linear combination is a non-zero row, which means that the rows are independent. So we have to study arbitrary linear combinations of the rows. Right. So by the way, this previous thing that we did, this proves an interesting property of determinant, that if you take equi-sized minors, all of them, like as formal polynomials, then they are linearly independent. They are linearly independent polynomials, right, which is a non-trivial fact, right? So if you take all the, for example, first order, all the d minus 1, order d minus 1 minors, I mean, even showing that these d choose d minus 1, which is d many polynomials, they are linearly independent, right? This seems non-trivial, and we are showing it actually for any order. But we have to show more. We have to actually talk about its evaluations in a smaller space, subset of points. So okay, so we'll prove a stronger property than what I just said. Okay, so we'll show that if So you have a symbolic matrix X or big X, and look at all the R cross R minors of this. Okay, and take an arbitrary linear combination of these minor polynomials. Let's call it F. Then we want to look at the probability that F alpha bar is non-zero. For a random point. So what is this probability?
I'm not sure I understand something.
Mhm.
So, when you're taking the b minus 1 plus b minus 1 minus,
Right.
you're saying it is hard to show that they're.
No, it is a non-trivial fact. May not be hard to show.
I mean, they would have different monomials, right? As if you look at them as polynomials. I mean, if they take a symbolic matrix, if you looked at different monomials, right? I mean,
So you are saying that the support is disjoint.
one of them would have a monomial that none of the others would probably produce because.
No, is it probably, or are you saying that the support is disjoint?
Yeah, that's what I'm saying. I mean,
So from a monomial you can deduce.
The 1 cross 1 minor will be the determinant of the lower triangular matrix,
Mhm.
and then the 1 cross 2 minor, it will not have any terms of
Yeah.
x to I.
So that could be a possible proof. Yes. You have to check it, but so using such things, yes. So which I think is also what we did here by picking alpha bar. Yeah, but then, so if we have indeed shown that the minors are linearly independent, then this f cannot be a zero polynomial ever, right? If you are taking a non-zero linear combination of the minors, f will always be a non-zero polynomial. It is also multilinear. So then by Schwarz-Zippel we already get this right. So even when Q is 2, the worst possible case, F field is GF2. Even then we will get this probability to be half, right? And actually that will be enough, I think, for the calculations. Yeah, so maybe I don't need this claim, but I'll prove something better, 1 by 4. But I don't think this is important then, because already at this point I could have done claim 1 with probability half.
That's better, right?
No.
I think
Yeah, some. So the Schwarz-Zippel that we have discussed before is for the total degree.
Cable Q, right? Schwarz-Zippel.
You mean R? R by Q. In claim 1, R cross R.
R by Q.
But individual degree is only 1. So can't you get 1 over Q?
We need total degree.
Yeah, that is what I'm not sure.
Total degree. Yeah, I think we need total degree.
Yeah, so the version we have proved of Schwarz-Zippel requires total degree. But individual degree.
individual degree, there's the combinatorial thing, right? No
Hmm. Yeah.
Something, but that just talks about one
Okay.
polynomial.
Yeah, so maybe it is not what I think. So we'll do this formally. We'll show that the probability of f non-vanishing is at least 1 by 4. Okay, before proving the claim, what does the claim imply? So this implies that the rows of your matrix Mk now with this smaller subset A that well, first of all, they are linearly independent. Moreover, their linear combinations has a number of zeros less than equal to 3/4 of q raised to n. This is just because of this probability calculation. The probability is saying that being 0 is less than equal to 3/4. So when you take an arbitrary combination of the rows of matrix MK, what do you see? You see basically evaluations at alpha bar in A. Right? A is a subset of the whole space. So it remains true that the number of zeros cannot exceed 3/4 q raised to n. So number of zeros is less than equal to 3/4 qn, which implies that number of non-zeros is at least the size of A minus this worst case 3/4 q raised to n. And here you use that A is large, right? So A is 1 minus small o of 1 q raised to n minus 3/4 q raised to n, which is q raised to n times 1/4 minus small o of 1. But small o of 1 is tending to 0. It is in particular smaller than 1/4. That's all actually we needed. So this is positive. Okay. So in other words, any linear combination of the rows of the matrix is a non-zero vector, which means that the rows are independent, which means that the rank is as claimed, d choose k square. Right? Is that clear? So we'll just show claim 1 now. Well, so the base case of claim 1 is when R is maximum. So when you are looking at determinant itself, right? So what is the probability that determinant at alpha bar vanishes or does not vanish? Yeah. So Schwarz-Zippel will give you, as you were claiming, d over q, and q is very small, so it's meaningless. Right? How do you get 1/4 or 3/4? So that needs a proof. No, there is no possibility of boosting. This is a, yeah. So let us do that. That already is non-trivial then. So all these problems are happening because q is extremely small, right? Otherwise these things were trivial. And the other parts of the proof will fail if q is large. So we have to break this cycle. So first we prove a base case. Let's call it claim 2. So here we will show that the probability when f is determinant being non-zero is 1/4. So trivial would have been equal to 0 is d over q, so 1 minus d over q. This would have been trivial, but this is actually now a negative number because q is much smaller than d, so this doesn't work. Yeah, so Schwarz-Zippel is actually not applicable. Then we have to work harder. In fact, we will use properties of determinant and permanent. Well, so determinant of alpha bar being non-zero means that alpha bar represents a non-singular matrix, right? So how many matrices are there? Just do the count. So number of invertible, this is alpha bar represents an invertible matrix. So number of invertible matrices in FQ D cross D is, so who knows this count? There is a formula.
P to the n times P to the n minus
No, there is no P.
Q,
Uh-huh.
Q, yeah.
So Q raised to D minus 1, Q raised to D minus Q.
We just count the number of matrices and then show that all the values you'll get the same number of matrices.
So this is just counting the rows. So first row has Q raised to D minus 1 possibilities, and once you have fixed the first row, then the second row is remove the Q multiples of the first row. So second row possibilities become Q raised to D minus Q, and so on. That's it, right? So this gives you the probability now. So the probability is equal to this number divided by Q raised to D square. Right. So it's 1 minus 1 over Q, then 1 minus 1 over Q square, and so on. Which now we want to lower bound by 1/4. So what is that? Why is that? Q is at least 2, right? So you get 1 minus 1 over 2 raised to D. So in fact fix Q to be 2. So what do you get? That's the worst case. Right, and this is 1/4, lower bounded by 1/4. In fact, strictly greater than, right? Greater than 1/4. Is that clear? That's the proof. But what will you do with the permanent? What is the permanent analog of this? Permanent of alpha bar non-zero has no good interpretation. So what will you count? So let's leave it as an exercise. For permanent. So I think for permanent, the number of alpha bars such that permanent doesn't vanish comes out to be the same number. You have to use the definition of permanent to get to this. Let me skip that. Yeah, so now with this base case in mind, let's go back to the proof of claim 1. So now let the linear combination, FQ linear combination of R cross R minus determinant D of a formal matrix X. R here you will take now less than D. Be f x bar equal to so we will take we are taking a linear combination of the minors mi's of the matrix x, and we want to divide this into two parts. So in one part the minors are with respect to I mean the first row is used. So these are the minors with row 1. So row 1 in mi, and these are the remaining ones. Row 1 not in mi in mj. Okay. So since row 1 is in mi, we can expand mi with respect to the first row, right? With respect to this x1 star variables, we expand mi. Expand mi by row 1. So what will you get? F is sigma, you have x1 star, so let's say x1i times mi prime plus, right, and let's the remaining is some kind of garbage part, m prime prime. So these mi primes are since we get mi prime when we expand this, right? We expand mi with respect to the first row of determinant of x. So this expansion will reduce the order of the minor, right? So these will be should be now r minus 1 minors. So order r minus 1 minors. And what is m prime prime? Actually, mi prime is not itself itself a minor. It's a linear combination. So linear combination of order r minus 1 minors, right? So these CIs will contribute, and we have taken out x1i. This m prime prime are those is the part which is free of the variables that appear in the first row. So this is free of x1j variables. J1 to D. Okay, so this is the decomposition. So what can you do with this? This is the nature of your f. And so you want to show that when you evaluate f at a random point, it will not vanish with probability 1/4, right? So how do you get that? We want to use the fact that m prime prime is somehow disjoint from this first part. This mi prime is also free of x1j variables, right? So both of them are free of x1j variables. So because x1j variables have been isolated, they have been brought out. Yeah, so the idea would be that except the first row, the other rows you fix randomly. So when you do that, it is possible that all these primes and prime primes vanish. That will be a bad case. If not, then you have a linear function in the first row variables, and you know that it will not vanish with probability 1 minus 1 over q.
You could have this kind of a union bound, right? Because I believe the elements inside M double prime and Mi prime are also Mi prime and M double prime might be, but that could be a problem. But then you could work with one of them. As long as the Mi primes themselves don't vanish, we are fine, right?
Formally, you mean, or with after substitution?
After substitution. So let's say the Mi primes are the ones that
No. If even if all the Mi primes vanish, if M prime prime doesn't vanish, then F doesn't vanish.
yes.
So
What
the only problem is when Mi primes and M prime primes, all of them vanish at a point. Then you don't have anything to argue. I mean, then obviously F is also vanishing. X 1i will not help. That's the only bad case. So we have to use induction and this structure to finish the proof. No, you are picking a random point, so it could vanish. It's an arbitrary point, alpha
but
bar.
I think that is very low probability.
Sure, yeah, right.
Every determinant vanishing, and it probably will be something like a
Mm-hmm.
product, but if it would be something like a product if and only if those were independent, and that is why I was saying like maybe work with just M double prime or just Mi prime, because then we'll probably get variable disjoint things, so we could probably make it
Mhm.
independent.
One thing we can assume here is that these Mi primes, at least two of them are at least what do you want to say, that
Mi prime should be variable.
I mean, since we have covered the base case, we'll assume that F is a linear combination of at least two minors. At least two R cross R minors. And hence we can assume that at least one of the Mi primes is non-zero formally. Okay. So what will you do when all these MIs were, this part was 0 to begin with? There was no rho 1 minor, no minor involving rho 1. Well, rho 1 was just arbitrarily chosen. You whatever row appears, you pick that, right? So hence we can assume that in this first part, something is actually appearing. So one of these Mi primes we can assume is non-zero. I think that is all I need to assume. So probability over the space Fq to the n such that F at alpha bar is non-zero. Okay, this is the same as the probability that alpha 1i Mi prime at alpha bar plus, so just that decomposition at the point alpha bar we are looking at, this is non-zero, obviously. And I want to say that this probability is at least the probability that the first part is non-zero. Is that clear? Why is that? No, we have evaluated the variables at alpha bar. Yeah, but I think it uses what you are saying. That is the proof. Well, if m prime prime is vanishing at alpha bar, then these two probabilities are actually equal. So the only case you have to look at is what if m prime prime is non-vanishing at alpha bar, right? So it comes out to be a number, but it is free of these alpha 1 i's. It's independent of that, right? So then you should think of alpha 1 i's as not yet fixed. Yeah, they are actually variables. So this sum has to take this particular value. So that probability will not depend on the value. So you can assume the value to be as well 0. Okay, that's the proof of this. Did we just show that it's equal and not greater than equal to? Anyways, this trick has a name. It is called Coutis's trick. So right, so what have we reduced our problem to? So the latter expression involves only minors with rho 1. So we can repeat this trick, right, and reduce to an expression where there is some other row, say rho 1 and rho 2 both are present, and rho 3 dot dot all the rows are now fixed. So your minor is fixed. So you have reduced to a single minor case, which is the base case. So repeating this several times. So basically, I think r times. We end up with a single minor expression. So that was covered in claim 2. So the probability is hence the same as shown there. Is this clear? So this trick is used to reduce the number of minors in the expression. Eventually go to the base case. Sure, if you look at mi prime, then yes, but by expression I mean the sum. The sum is still on the r cross r minors. Right, the sum is just a reformulation. So the sum remains. All we have done is we have eliminated those minors that do not involve rho 1. And yeah, this can be a strict inequality in the case when mi primes vanish at alpha bar, right? So if they vanish, then because of that, the first probability will already become 1. So it's a strict inequality, but it's at least we at least get greater than equal to in all cases. Right, so claim 1 is shown, which we have seen discussed before. The measure exactly, actually, not just a lower bound. So when you look at this MK matrix of the determinant, for columns less than the whole space fq to the n, the rows are actually linearly independent. It's a non-singular matrix. So again, this proof you can complete for permanent. You can repeat this for permanent. Okay, so eventually these properties and the measure, it is not able to distinguish determinant from permanent. Right, so we have proved lemma 1, which was upper bound on circuits, and lemma 2, which is lower bound on determinants. Right, so this is the right time to compare the two. So that will finish the proof. So assuming that determinant D has a size S depth 3 circuit over FQ, so lemmas 1 and 2 imply something about the parameter with tau is alpha times D and K is tau over 10Q. Till now we have not said anything about tau, right? So tau will be some multiple of D, multiplier is alpha. K we have fixed to be the maximum in lemma 1, which is tau over 10Q. We get that the measure on determinant, because it has a depth 3 circuit, it is smaller than SQ to the tau, which is alpha D, and by determinant's property lemma 2, this is equal to D choose K square, right? We get this. And now look at the endpoints. So you will get that S is greater than D choose K whole square times Q to the minus alpha D, right? And we have to see how good this is, because from the face of it, it may not be very good, because D choose K whole square is something like 2 raised to D, and Q raised to alpha D is also like, well, actually so we assume Q to be constant, then Q is like 2, so this is 2 raised to alpha D. So this is, then intuitively S has to be at least 2 raised to 1 minus alpha times D, right? So this suggests that if you take alpha to be a fraction, things should be fine, right? You take alpha to be a fraction, actually depending on log q. So you should take alpha to be 1 over log q. Right. So this is what this suggests, that you take alpha to be 1 over log q should give s greater than something like what we wanted. Right, but this is obviously not correct, because d choose k whole square is not 2 raised to d. Right, it has a complicated expression. So we have to do this then in more detail. So let us do that calculation. So what do you know about binomial estimates, Stirling's approximation? Yeah, but at least this back of the envelope calculation tells you that there is no hope for q large. If q is really growing, then the RHS here is growing, so then it becomes hopeless, right? Then you will just get that s is greater than 1 or s is greater than 0. You will not get any meaningful lower bound. But for constant q, you have to work this out to find out what q will work. So for that we have to go into Stirling's approximation, which tells us that log of n choose epsilon n is what? Let me express in terms of Shannon's entropy. Where H2 is what is H2 epsilon? Exactly.
There should be 1 minus and not 1 minus.
Sorry. Right. So since it's a log, so basically n choose epsilon n is something like 2 raised to n. But if you try to pin down the factor that sits in the exponent, that is exactly Shannon's entropy. Okay. So depending on epsilon, if you take epsilon to be too high, like 1, then you don't get anything. And if you take epsilon to be very small, like 0 or close to 0, then again you are in trouble. But if you take epsilon to be somewhere in the middle, like half, that gives you the most mileage. Okay, that takes you to 2 raised to n. And there is this error term of log n, which just we can ignore this, because the main term is n, so we can ignore log n. Yeah, I think today also we cannot finish this. There are some calculations remaining. So we'll do this on Saturday. I hear that Saturday is a class, working day. Wednesday, right? So let's finish this and start another lower bound. Any questions?